Hello, everybody. We're going to continue our conversation about interpolation today. We ended last class talking about some of the drawbacks to Lagrange interpolation and how, especially if you have a lot of data, that can cause, because of high degree polynomials and the nature of how they behave, a lot of weird oscillations and different sorts of things that mean that the shape that you get is not reflective of what you might want it to be. There are some different kinds of tools that we can introduce, and one of those is to consider different kinds of information with regards to each point, not just the heights, but also different information. So we're going to talk about that today. That might help to get the shape a little bit better and kind of pin that down at every one of those nodes where you have some data in order to get a better result. And from there, we're going to be talking a little bit more about other kinds of polynomials in the next couple lectures. But let's start with this one. This is the concept of Hermite interpolation. And Hermite interpolation is kind of exactly what I'm saying. It's fitting different kinds of data, not just heights, at every data point. So in fact, what we're going to be thinking about is including the slopes that we desire at every single one of those data points. Okay, so I want to fill in the next blanks, and then we'll talk about it a little bit. If we have not just a height, but also a slope at every single point, that means we have double the information that we usually would. And what that requires is a polynomial with a higher degree. Why? Well, okay, I want to step back for a second and think about where we're at. So I think that it's pretty easy to buy that if you're given two different data points with two different x values, there's a unique straight line or first degree polynomial that goes through that. If you have three different data points, there's a unique parabola that goes through those three. The reason is not necessarily because you have three different x values per se. The reason is because you have three different pieces of information and three different coefficients that you would need to pin that down. Think about that. To obtain a polynomial that passes through those exact 3 points with 1, 2, 3 different heights, I need 1, 2, 3 constants in that polynomial to determine that polynomial uniquely, right? If you think about a parabola, that's ax squared plus bx plus c. So it's really just the fact that you have 3 different pieces of information you're trying to incorporate at the same time. So in general, you need a polynomial with that much flexibility, 3 different coefficients. So you see, with a Lagrange polynomial, and if you had, say, 2 different points, you only need 2 different pieces of information to get a function that passes through those 2 points. You need a linear relationship. Y equals mx plus b. Right? But for a Hermite polynomial, not only do you have slope height data there, you also have slope data. So you have 1, 2 pieces of information associated with the first point, and you have 1, 2 pieces of information associated with the second point, and therefore you have 4 pieces of information, even though you have just 2 points. So you would need, so 2 heights and 2 points. This is, what do I want to write here? I want to write, so 4 pieces of information. 4 pieces of information, and with 4 pieces of information, you need a polynomial of degree 3 because there are 4 coefficients in a general cubic function, right? Ax cubed plus bx squared plus cx plus d. And that's why you get this higher degree polynomial. But maybe it's one where we're guaranteed to have some control over what exactly that polynomial is doing in terms of its slope at every single one of the points. So you can get maybe a more accurate result for certain applications. Now, the big question is, how do you do this? Like, what is the format of a polynomial like this? Because it's got to be complicated. And it is a much more complicated form. So let's chat about that. Suppose we have n nodes, x1, y1 through xn, yn. So this is familiar. We have like this data that we know. But in addition, we also have slope data. So to x1, y1, we know that we want slope m1. For x2, y2, we know that we want slope m2. All the way through to mn. So I've doubled the data. Okay. Here is this nightmarish form. It's very complicated, but you'll be able to look this up. if you are tested on it or anything like that, so I'm not too worried about that. Okay, here's what it is. It's two different sums, and you want to look at this. There are the different xi values right here and right here, and it looks like there are a few other quantities involved. You can see the yi values. You can see the slope values right here and right there. But there's also a familiar character coming back. We have the Lagrange basis functions in play as well. So those are the basis functions that we defined at the start of Lagrange polynomials. They're exactly the same, but they appear in these functions either squared, right here and right here. Okay, that's weird, but the first basis function, the second one, all the way through the number of points, as well as the derivative of it. But the derivative evaluated at the particular node, whatever that might look like. So a little bit interesting there, but we're going to work with that. Okay, it looks crazy, and if you just looked at that and trusted that it does its job, okay, cool. But what I have for a first example here is actually not putting this formula to work. It's more just an exercise so that we can believe in the formula, right? We need that this formula will give us a function, give us a polynomial that will pass through all the data points. So I need this formula to be such that if I put in xk, I get out yk. I want that the formula is completely accurate at each node. Therefore, it becomes something that interpolates all that data. That's what this exercise is. It's something that will get us to believe that this formula is what it should be. Okay, so we're going to verify, given the above formulation, that h of xk is equal to yk for each node xk, yk, i.e. that the resulting polynomial does pass through each node. Okay, so we need to make sure that if I plug in xk, we get out yk. So let's plug in xk. It looks intimidating, I'm not going to lie, but based on the definitions of those Lagrange basis functions, we're going to be able to make some things melt down pretty quickly. So check this out. We get h of xk is equal to, there's a sum, I equals 1 to n. I'm just going through, I'm subbing in xk for x. Okay, it looks like this is, oh, not quite. I need this to be li prime at xi. And then this whole thing is li squared at xk yi. And then over here, if I sub in x equals xk, I get xk minus xi, li squared of xk mi. Whew, okay, so a couple things I just want to point out because it can be a bit of an alphabet soup. Up here, these x's are just x's. They're part of the polynomial, right? The different powers of x's appear, right, by whatever the Lagrange polynomial is, and so on. The x's are there. Now I've subbed in xk. So everything here is really numerical, right? xk minus xi right here. This is a Lagrange function evaluated at a particular node. This is a Lagrange polynomial evaluated at a particular node, xk. Think of xk as a number, okay? I want to remind you of the fundamental property of those basis functions. So I'm going to say right up here, we're going to say recall that li of xk is equal to, there are only two possibilities. This goes back to the very beginning of our discussion on Lagrange polynomials, but those basis functions are equal to 1 if the I matches the k. So the first Lagrange basis function is equal to 1 if you sub in the corresponding point, okay? So 1 if I equals k, and it equals 0 if I does not equal k. So this li of xk, li of xk, li of, well, maybe xk, maybe not here, li of xk, like these things are equal to either 0 or 1. There's nothing else but those. And that's going to help us to kind of peel this apart. So let's use this I'm going to put this in a little bit of a cloud, and then we can think about how this is going to go in each one of these sums. So don't be intimidated, but I understand if you are, because it is a little bit gross, but check this out. If Li of xk is equal to either 1 or 0, I want you to look at the sum. This sum is going to go through every single value of I. K is some fixed value. It's the second node, it's the third node, it's the kth node, whatever one it is. So if I go through this sum one value at a time, that is plug in I equals 1, plus plug in I equals 2, plus plug in I equals 3, all the way through to n, at some stage, the I is going to equal the k, right? I'm going to get to that node that I'm interested in, and I is equal to k. If for all of the other values of I, though, they're not going to match. So I want to think about that. Li of xi, Li of xk, that's what I want to look at here. This quantity right here. This is going to equal 1 if k is equal to I. I'm going to say if I is equal to k, rather. I know it's a weird thing, but the i's are the thing that's going through. Or 0 if I does not equal to k. So essentially, the reason I'm picking on that piece is because, right, this is going to be 0 most of the time. This quantity is going to equal 0 whenever the I is not equal to the k. And therefore, I'm going to get 0 times all of this junk over here and the yi. It's going to kill the whole thing for every single one of those terms except for a single one. And that is the case where I is equal to k. Right, okay. So the only term that could survive is when I equals k. Because all of the others are just going to be flattened to 0. Okay, same sort of thing over here. I'm going to say ditto over here. But there's something that's going to happen in each one of those. So yeah, I want to actually consider what happens now when I plug in, well, the kth one in each sum. Because all of the others are just going to be dead. We're going to have 0, and we're going to have 0. And there's no point in even writing them down. So actually, I can extract from each sum the case, the single I equals k term, which gives me just one term to consider in each one. So this is going to equal, only the kth one survives. I'm going to write this down. 1 minus 2 times xk minus only the kth one. So it's when I equals k, that means I get here xk minus xk, which looks also like more stuff is about to die. I'm going to have lk prime at xk, and then this whole thing is going to be multiplied by, well, when I is equal to k, this li squared thing is going to be 1. So that's what I get here, and I get yk as a result right there, because the kth one survives. Only the kth term of that first sum survives. Same thing with that second sum. Only the kth term survives, but I think that you'll see pretty quickly what happens here. So xk minus xk is what we get. And li squared xk, if the I is equal to k, I get lk squared of xk. That's going to be 1 again, based on the definition. And then mk. Okay, so I'm going to write a little bit of note. I'm going to write it on the side and say only the kth terms survive with an exclamation mark, just to remind you of what's going on here when you go and look back over this. But of course, xk minus xk is itself 0. So that means this term here is equal to 0, which kills this whole piece. And look what we're left with. We're left with 1 times 1 times yk. Over here, xk minus xk, also 0. So this whole term is always gone completely. And what we're left with is nothing more than yk, which is what we were looking for. So you can see, if you understand and you are comfortable with the idea of these basis functions and their different properties, it's actually just a couple of lines to show that, yeah, when you put in xk, you get out yk, which is a good thing, because if that wasn't true, the corresponding polynomial wouldn't be going through the right points. So it is also possible to prove that whenever you take the derivative of this thing, God forbid, because it looks like it's going to be a nightmare to calculate a derivative of something that looks like this, you can show that the derivative at each point is given by the mi's, which is the other piece that we would need. But I decided not to do that here because it's really, really messy. This is messy enough. So if you're really ambitious, you're really excited to try and dig into this, I welcome you to try that as well. I've written it down a couple times in my life, and it's possible to do, but it's just ugly. So optional extension for you to try craziness. Okay, well, let's check this out. We have the ability now to maybe use this formula if you believe that it is going to interpolate all those different y values and have the right slopes, which you can verify for yourself. Then maybe we can to use it for a different sort of example. So I have one last example here to sort of finish up. I'll mention coding in just a sentence or two afterward. We want to find a Hermite polynomial that interpolates the function y equals ln x at the points x equals 1 right here and x equals 2 right here. I've actually gone forward and graphed this, okay? I've graphed the answer, and you can see for yourself what that answer looks like. We have just 2 points here, so 2 points of information, but we are using both the heights and we'll be using the slopes. And so we're going to have 4 different pieces of information that's going to yield a cubic function. And just look at this cubic. This is a cubic that goes through, has the same slope as the ln function at this point, keeps on going, has the same slope information as the ln function at that second point, and the heights of both as well, and then continues onward. And oh my gosh, that function, that cubic function that does that, does such a tight job of approximating the function ln of x, especially between the two, but also in a neighborhood around them. So it's a really, really powerful technique. It just uses a little bit more information. So okay, let's think about what we need here. We're going to need some Lagrange basis functions. We're going to need slope data, because the slopes up here in this, we need them to be a part of this whole thing. So let's come up with a little bit of a graphic here. So we have y equals ln x. We have different values. So we have, maybe I'll write this down in like a chart sort of thing. X values, y values, and slopes. Okay, so the different values that we have here are going to be x. I guess we can start with x1 and say x1 equals 1 and x2 equals 2. The y values are simply those values that you get when you sub them into the ln function. So y1 would be ln of 1, which is 0. And y2 is the ln of 2, which is, well, whatever it is. The slopes, of course, we're going to need the derivative. So why don't we just write that down for a second? We see that y prime, simply enough, is 1 over x. And so the slopes that we want at each one of those points that are being interpolated, we're going to have m1 equals, well, when x is equal to 1, the slope is equal to 1 over 1, which is 1. And when x2 equals 2, m2 is going to equal to sub the 2 into the slope formula, and you get 1/2. So I know that I want the function, the polynomial that we get, to pass through the point 1, 0 with the slope of 1. And we want it to pass through the point 2 ln 2 with a slope of 1/2. That's the polynomial that we'll be looking at. And as part of this whole thing, we need those basis functions. So let's do that as the next step. Construct our basis functions. Because we see that those are in the formula that we need. And those are not hard to find, right? L1 of x is equal to, remember how this goes, consider all of the other ones. So the x2 it's going to be x minus x2 over x1 minus x2. So I think we get nothing more than x minus 2 over 1 minus 2, or negative x minus 2. So this is L1 of x, and similarly L2 of x. Same sort of deal, but we flip things around. It's x minus x1 over x2 minus x1. So I think we get here nothing more than x minus 1 over 2 minus 1, which is nothing more than x minus 1. Okay, so this is L1 of x, this is L2 of x. And before we move on, there's one other piece that belongs in that formula. If I scroll back up, notice I need the derivatives of these things too. I need the derivatives of the Lagrange functions. So that's going to be helpful for us as well. And so let's find those. Luckily, not hard. L1 prime of x is equal to negative 1. Just thinking about what calculus does to that thing. And L2 prime of x, which also appears is equal to positive 1. Just like that. So really simple, because the Lagrange basis functions here are just linear, right? So the derivatives should be constants. But in general, you could get functions of x here. So that's going to be useful to us. Okay, so this here is L1 prime. This one's L2 prime. This one here was L1. This one here is L2. I'm going to rewrite the formula, and then we're just going to use it to the best of our ability. So let's try our best here. The formula is... I've rewritten it on a piece of paper here, so I'm going to just refer to that for a second. Super fun, right? All right, h of x is equal to, and it was the sum, I equals 1 to n, of 1 minus 2 x minus xi. Li prime, evaluated at xi, and then we multiply that by Li squared of x times the height. Okay, and we add those all up, and then we add another sum, and it's this. X minus xi, Li squared at x, and then slope data. Okay, so we're going to go through. We only have 2 points, so we're going to have 2 terms from each one of these, but we're going to be very careful in what we do. So let's do our best. So h of x equals, let's do the first one first. So when I is equal to 1, let's go through and plug in our different values. So we have 1 minus 2 times x minus x1. X1 is just 1, if I just scroll up a little bit. So this is going to be an x minus 1 here, times L1 prime at x1. So L1 prime is negative 1, and at x1 is just going to be negative 1 as well. So I'm going to put that there, negative 1. Okay, that is going to be multiplied by Li squared of x, so L1 squared. L1 squared is going to be minus x minus 2 squared, because that's L1 of x, and then I multiply by y1, and y1, it's 0. So all of that work so far for nothing, but that's what the first term is going to look like, or how it would look like. It's going to be worth nothing in the end, but heck, that's just how it goes sometimes. Let's do the second term. The second term will be 1 minus 2 times x minus the second x value, so x minus 2. I need to multiply by L2 prime, evaluated x2. L2 prime is 1, so I just get a 1 here. Okay, I multiply that by L2 squared, and L2 squared is this thing squared. So I get x minus 1 squared. And I multiply by y2. And y2 is ln 2. Okay, so that seems like it's going to be a term that that is non-zero. And it looks like it's going to be a cubic. You can see that because I have an x times an x squared here. And so that should make a lot of sense. Because we were expecting a cubic, right? Let's do the second sum here. So I'm going to have x minus x1. x1 was 1. So x minus 1. We're here right now. I need L1 squared. So I need L1 squared is going to be minus x minus 2 squared. So that negative sign will be squared away because that's L1 squared. And I need to multiply that by M1. And M1 is 1. Okay. That's what the next term looks like. And then finally, I need that last term when I is equal to 2 here. So that's going to be x minus x2 is 2. I need L2 squared of x, and L2 squared of x is just x minus 1 squared. And I need to multiply that by that same slope value m2, and m2 is going to be 1/2. Like that. Phew. So I'm not going to bother to collapse this down or anything like that, but you can kind of see how this is going to work out. We end up with this quantity right here. These three terms that remain added together. I mean, I'll write down the whole thing, I suppose, because that one term, it just evaluated to 0, but that's what it looks like. And you can see that we get a cubic, and that's going to be just the right cubic that passes through those 2 points, but also incorporates the slope data at those 2 points. Cool. So it's a little bit much, right? But it's about careful reading, making sure you process the formula properly, not making any mistakes along the way. It's easy. I wouldn't be surprised if there are issues here with this, and I'm sure you could simplify this down if you wanted to. Okay, so the last question, as I said, just a couple of sentences here. Coding Hermite seems like a nightmare, right? You need to be able to find a way to code each of those basis functions, and then to be able to call them and include them within each of those terms as necessary. Coding a Hermite polynomial, though, is nearly required if you want to include data at more than 2 points. Imagine trying to do this with 3 or 4. Like, that's crazy, right? It would take a ton of work. You'd have to take derivatives of the basis functions, and that's going to be ugly as well. It would be really nice if you had a computer to do that for you. You're totally welcome to challenge yourself and try to put together MATLAB code that does this, but we'll just say that it's a little bit beyond, okay? That would be extension. I would definitely want you to be able to look at existing code and be able to interpret it and say, oh, Matt, you're doing a Hermite sort of thing there because you're taking into account slope information, and that big ugly formula, I tried to block it out of my memory, but I couldn't. I recognize that as being Hermite. So I would want you to be able to recognize it, and so it could be helpful for you to spend some time and try to figure out how you might want to code it. But I'm never going to ask you specifically to code this, especially like in a test or anything high stress, because it's so picky, okay? But I do want you to understand the concepts behind this and why we might want to use this, how it differs from regular Lagrange interpolation, and go from there. So that is pretty much that for that concept. Now you understand what a Hermite crab is all about. But overall, hopefully you're able to follow along okay. You're understanding how to use these polynomials and how they differ from Lagrange. In the next lecture, we're actually going to construct some different methods of putting together polynomials that interpolate using a different format entirely. It's really interesting. It's kind of fun, I'm going to say, but it's completely different and it does not use those basis functions. And then after that, we're going to talk about another method entirely of really useful interpolation. So I hope you'll join me, and I'll see you soon. So take care of yourselves.